Right, hiya Toast, this is Mr. Lim here, and today we're going to be discussing my 100 subscribers, woo! Now, we're going to be talking about this last question on the extended response, okay, about the theories of acids and bases. So, what is it actually asking you to do? Okay, so what we need to do is make sure that we actually understand the theories of acids, these three theories of acids and bases. So, Davy, okay, proposed that acids, substances that contain replaceable hydrogens, and then that hydrogen that can be partly or totally replaced by metals, and bases were substances that reacted with acids to form salts and water. So that's the Davy. You've got a definition for acids, a definition for bases. You've got the Arrhenius model, which is soluble acids and bases only, right? And identified acids as substances which produces hydrogen ions in solution, and bases that produce hydroxide ions in solution. Okay, and Bronsted-Lowry finally described acid-base behavior in terms of proton donors and proton acceptors. Okay, so these are our little 6 definitions of acids and bases depending on which type of model that you've got. All right, and so this question is asking in the extended response, you're supposed to do a little bit of research on these. For each of the substances below, use chemical equations and chemical reasoning to classify the acids as substances as acidic, basic, neutral, or amphoteric, amphiprotic substances. Okay, so acidic depends on the definition that we've got up there. Right? Basic also depends on the definition that you've got up there. Neutral means that you fit neither under the category of acid or base. And amphoteric means and amphiprotic means that you can act as both an acid and a base, right? So we need to be able to work out what each of those substances is based under those theories. Now, the important thing to remember is that you may not be able to classify certain things under certain models, right? That's why we have different models, or we've developed different models over time, because the old model sucked, the new model is better, right? So that's why we even bother discussing this idea. So let's have a look at this one here. We're having a look at these things under these different models here, okay? So HCl under Davy. Let's have a look at that, okay? So Davy defined acids as substances that contain the replaceable hydrogens that can be totally or partially replaced by metals, okay? So hydrogen chloride gas, if it reacts with a metal, will be replaced by that metal and produce hydrogen gas. So it's effectively replaced by things. So for example, HCl gas plus a bit of Mg solid will turn into MgCl2 and hydrogen gas, and after a bit of balancing, that is an acid-base reaction under Davy. Okay, that's fine. Okay, however, under Arrhenius, which says that only deals with soluble acids, right? For all intents and purposes, because this is not in a solution, you can't define this under Arrhenius. Okay, if you were to take that HCl and dissolve it into water and produce hydrogen ions, then yes, you could explain it under Arrhenius, but not under its current form in a gaseous state, right? So that hydrogen chloride gas is not classified as an Arrhenius base because it does not produce soluble hydrogen ions and therefore cannot be classified as an Arrhenius acid in gaseous state. Under Bronsted-Lowry, however, hydrogen chloride gas can be identified as a acid, right? Because under Bronsted-Lowry, acids are proton donors, all right? And so they're proton donors. All you got to show is that this thing donates a proton to something else, okay? So I could even do this with water, okay? It's going to donate that hydrogen to water. That's not going to be gaseous, it's going to be aqueous. And it's going to form Cl minus ions, and I don't need that 2 as a coefficient. And I think that's it. Okay, so under Bronsted-Lowry, HCl gas can act as an acid, as a proton donor. Okay, and then remember, under Bronsted-Lowry, you also need to identify conjugate acid-base pairs. Okay, so you've got one pair there, one pair there. What's the acid, what's the base? So this is the acid, this is its conjugate base. Oops, conjugate base. And this is the base, and this is its conjugate acid, right? And so you need to be able to do that for each of these. So let's go walk through some of these other ones, okay? Let's deal with, what next? H3PO4, okay? So H3PO4, can it act like an acid under Davy? Well, when it reacts with a reactive metal like sodium, it is going to in fact produce hydrogen gas and sodium phosphate. Yeah. Okay, need a bit of balancing there, so you're gonna need two of those, 6 of those, and 3 of those. All right, so that's what it would be for a Davy reaction, where you react with a metal to produce hydrogen gas. So yes, this can act like an acid for Davy, right? Can it act like an Arrhenius acid? Yes, it can, because you can propose that this substance here is actually H plus ions and phosphate ions. Okay, that would show that it is an Arrhenius acid. All right, can you also show that it's a Bronsted-Lowry acid? Yes, you can. Okay, so if you were to show that it's a Bronsted-Lowry acid, then what you would need to do is show it donating a proton to something else. Okay, so if we were to say that this substance, and especially because it's a weak acid, that's why we keep it together, if we were to add it to some OH minus, when I say keep it together, I mean don't split it into H plus and PO4 3 minus. Okay, add it to some OH minus, that would turn into H2O and PO4 3 minus. I'd need 3 of those and make 3 of those, and I don't need that coefficient of 2. And that would be the phosphoric acid acting as a Bronsted-Lowry acid, okay? Because you'd be able to see that, yes, okay, it's donating a proton. What's it donating a proton to? It's donating a proton to the OH minus, turning it into water. Okay, so this would be the acid, this is its conjugate base. Well, technically, that's not its conjugate base, it's the third conjugate base. Might be a bit easier if I showed this as the single ionization with the H2 here, H2PO4, right? So that's its conjugate base, and then this one here, this is the base, this is its conjugate acid. So yes, the phosphoric acid can be explained by all 3 of those theories, all right? The NH3 can't be explained by Davy, because Davy classifies bases as things that react with acids to form salt plus water. However, NH3, especially the gaseous form, if it was to react with an acid like hydrochloric acid, would form ammonium ions and chloride ions. You've got the salt there, but you're not forming what? You're not forming water. All right, and if you're not forming water, then you're not classified as a Davy base, because you're substances that react with acids to form salt and water. And so because you're not forming any water there, this NH3 is not a Davy base, all right? Again, nor is it an Arrhenius base, because it's only dealing with soluble things in aqueous state, right? But however, it is a Bronsted-Lowry base, because it has the ability to donate or accept a proton, and in this case, it's accepting a proton. Okay, so I'll have one pair there and one pair there. This is this is the base, this is the acid, this is the conjugate acid, and this is the base, a conjugate base. Okay, so that is NH3 gaseous. However, if we were to deal with this as NH3 aqueous, okay, aqueous, okay, then again, it still wouldn't act as a Davy base. It still wouldn't act as an Arrhenius base because Arrhenius bases make OH minus ions, or provide OH minus ions, right? Which produce hydroxide ions in solution. Actually, it does, but it's a bit hard to see how it does so, right? So NH3 does actually produce OH minus ions in solution, but it does so only by reacting with water. Okay, so the NH3, where's my thing? NH3AQ with some water will form NH4 plus AQ plus OH minus. All right, and that means that it's making hydroxide ions in water, which means that it is a Arrhenius base. Oops. Yeah, why is my thing so slow today? All right, and it is a Bronsted-Lowry as well because you can identify those conjugate acids and conjugate bases pairs. All right. Pyridine, which is effectively a another form of this this NH3 of ammonia. All right, it is, I don't even know what pyridine looks like, but I know that it is based on an ammonia ion. Let's see if I can work out what it will look like. Okay, but yes, it's going to have an ammonium group on it. So that ammonium group is going to be in the form of a single NH there, and then it's going to form a benzene ring for the rest of it. Okay, so that'll be one there, one there, one there. Nope, that's not right. There we go. All right, and so that is going to be the structure of pyridine or pyridine. Okay, and what happens is that when it has the ability to accept an extra proton there and turn into a positive ion, right? So therefore that would be the structure of it as C5H6N positive, right? And so this substance, before you add that, has the ability to act like a well, it can't act like it's a Davy base because it's not going to form a salt and water because it doesn't have the ability to form water, right? It's only going to form an ammonium salt. The Arrhenius theory, yes, this thing could react with water, all right? It could react with water, and, well, I mean, it probably does react with water, and it's going to form OH minus ions and that this is how you draw it, with an N there, with a H and another H positive. All right, so that's how it would act like a Arrhenius because it's going to form the OH minus ions in solution, these OH minus ions. Right, so Arrhenius, and therefore, and also a Bronsted-Lowry, and hopefully you can identify the conjugate pairs by now. All right, H2O. Now we start to think about things a little bit harder. All right, H2O, it can act like a Davy acid. All right, it can't act as a Davy base, right? But it can act like a Davy acid, depending on what it is. Okay, so if you were to say that water was added to sodium metal, okay, it's going to form hydrogen gas and sodium hydroxide. Okay, two of those, and two of those. Right, that would be the Davy model of this particular substance, being an acid, all right, because it forms hydrogen gas, okay, and the Na has replaced some of that hydrogen, partially replaced some of that hydrogen, okay. Under Arrhenius, water would not, well, I mean, water does technically create a hydrogen ion and an OH minus ion in its self-ionization, right? So water could produce a H plus and an OH minus, right? And it does so to very small extents. So therefore, water can also be be represented under Arrhenius under a. Okay, so this one here is just a acid only, but this is an acid and a base. And what do we call this when it's an acid and a base? It is amphoteric, right? And under Bronsted-Lowry, it would also be an acid and a base because it has the ability to react with itself to form H3O plus ions and OH minus ions, which means that it's acting as an acid and a base, and it's accepting and donating a proton. All right. And if you hadn't worked it out, KCl is neutral. It cannot do any of these things, and so therefore it cannot be explained as an acid or a base under any of the models, or at least it's explained as neutral under all of those models. All right. So that's what you were supposed to do, showing things with chemical equations and chemical reasonings to identify these as acidic, basic, neutral, or amphoteric. All right. The only one in that list that was amphoteric was H2O. But there are other amphoteric substances out there. You just have to be able to accept and donate a proton. All right. So that's that. If you have any more questions, send me a direct message. Adios.